This is lecture 25, typedef. The C programming language provides us a keyword that is named typedef and allows us to provide a new name for an existing data type or a data structure. This example here is showing us that we can change the data type from unsigned char to utilize the single term byte. So we start with the keyword typedef, the data type that we're referencing, and then the new name for it at the end and our semicolon. So once we perform this typedef, instead of having to type unsigned char each time I want to create a variable of that data type, I can just reference the new word I created, or name, byte.
That's crazy.
And so here you can see I am declaring two variables of data type byte, and byte is an unsigned char. Best practices say that we should, when we do create typedefs, we should put them in all uppercase. This is the visual indication to a programmer that this is a redefinition. You are permitted to use all lowercase, but we should be careful so that we don't confuse somebody who is potentially reviewing our source code or doing maintenance on it. So let's look at a source code example here using the typedef. So I have a couple of varying implementations of this functionality. The first implementation is here where I've created a struct named books, and each book has a title, author, subject, and an ID. I can utilize this books struct. I can create a variable of my struct books. Again, I have to use two words to define my data type for my variable book. And then as a result here, I can populate my struct and each one of the members inside of the struct in the various opportunities of how we supply data to the members in a struct. So here, because I'm using a string, I'm utilizing that string copy function to copy the explicit text into each one of the string variables. And then the last one is just an integer, and so I can set that variable or member directly. Now, I don't want to have to keep typing struct books. So as a result, I'm creating a typedef. So I'm using the keyword typedef, the data type that I'm renaming, struct books, and I'm just going to use the letter B. So down here in my source code, you can see that I am now using the data type B and creating a variable called book1. So in the next portion here, I am using book1. I'm populating the members of the struct and printing them back out to the screen. The third option we have is to define the typedef and the struct all in one statement. So here I precede the keyword struct with the typedef. I have the name of my struct here, book2. I have my members of my struct, and at the very end, this is the typedef. So instead of typing out struct book2, I can just use the term or data type book, and it references this struct. So then I create a variable using that typedef book, and I'm able to populate the members of that struct and output them to the screen. You'll see that from the user's experience, there's no difference in the behavior. All three methodologies give us the exact same output. We have previously learned about using a pound define, and we learned about a pound define being a C directive, which allows us to create aliases. And so we've been using the pound define to create global constants in applications. There is a difference, though, between typedef and pound define. So typedef is actually limited to giving symbolic names to types, whereas pound define actually can be used to define an alias for values as well. So, for example, here I have two pound defines. I have one that is true and the value of 1, and I have one that is false and the value of 0. So it would not be appropriate to use the typedef functionality here. So type-def interpretation is actually performed by the compiler, and we previously learned that pound-defined statements are actually part of the preprocessor. So the type-def is very handy in allowing us to rename long data types to simplify our coding experience.
All right, let's take that quiz. I can't really do display capture because that would be cheating, and I don't want to get kicked out of college. So just gonna do that. And they are open note, by the way, so that's cool. Let's go. C program keyword type that allows software developers to give an existing data type a new name. Yes. Given the source code below, how should the developer declare a variable of struct_book2? Does all that apply? Ah, shoot.
word typedef, the data type that we're referencing, and then the new name for it at the end, and our semicolon. So once we perform this typedef, instead of having to type unsigned char each time I want to create a variable of that data type, I can just reference the new word I created, or name, byte. And so here you can see I am declaring two variables of data type byte, and byte is an unsigned char. Best practices say that we should, when we do create typedefs, we should put them in all uppercase. This is the visual indication to a programmer that this is a redefinition. You are permitted to use all lowercase, but we should be careful so that we don't confuse somebody who is potentially reviewing our source code or doing maintenance on it. So let's look at a source code example here using the typedef. So I have a couple of varying implementations of this functionality. The first implementation is here, where I've created a struct named books, and each book has a title, author, subject, and an ID. I can utilize this books struct. I can create a variable of my struct books. Again, I have to use two words to define.
Okay.
This is lecture 26, error handling. So the C programming language really doesn't provide direct support for error handling. But since it is a system programming language, it does provide access at a lower level in the form of return values. Most of the C or Unix function calls usually return a -1 or a null in the event that there was an error. But if we're using that appropriate header file, there is a global variable error no, and it would set that error code. So error no is a global variable, and it's part of the error.h header file. And there's other error codes that we can look at in the error.h header file. So as a C programmer, we could check the return values, and we could take appropriate action depending upon that return value. So if we are using that error no, it would be a best practice to initialize it to 0 at the time that we initialize our program, because we know that a 0 indicates a program ran successfully. So we have three different options here with our error handling. We can just use that value error no. There is a function p error, and there's a function string error. And so with the p error and the string error functions, they can be used to actually display a text message associated with that error no that we received. The p error function will display an explicit string that we pass to it, and then it'll append at the end a colon, a space, and the text representation of that error no value. The string error function, it returns a pointer to the text representation of the current error no value. So I have some code examples here where I'm going to simulate different error conditions. So the first one will be trying to open a file that doesn't exist. So I am going to use both of those functions, the p error and the string error, so you can see how they are used. And then one of the things that's very important is when we are using these functions, that the file stream we pass to it for output purposes is actually standard error. So far we've only used standard in and standard out. This is the first time we're seeing standard error. A common problem that happens in programming if we have any type of division being accomplished through variables is if we don't check to see if the divisor is 0, it creates a runtime error. And we can also set up our programs with macros, exit success being set to a 0 because we know again that a successful program execution results in a 0. And we could set up another macro as exit failure to a value of -1, which indicates that it was not successful. So here you can see I am including my standard io.h, my error no header file, and the string.h header file. So I'm going to link in that error no value or variable here in my main, before my main as a global variable. And then here in my first function is the no file. So I don't have an E drive on my computer, but I'm going to try to open a file from the E drive. So I set my file pointer equal to the f open function call, and it will fail. So in the event it comes back as null, I'm going to store in my local variable here, error num, the value that is passed into my error no. Here I'm using fprintf, and again I'm passing standard error instead of standard out, so I can utilize that error number. And this is my explicit string, and I'm just going to output whatever that value is. Here I'm using that p_error function, and this is my explicit text, and you'll see that it does append additional text that represents what the problem was. And then this is the third version here, where again I'm using fprintf, I'm using standard error. This is my explicit text, and then I'm going to get the pointer back to the string associated with that error num. In the event that I don't have an issue opening my file, I'll just close my file when I am done. Okay, so the error number I got was a 2. And this was my explicit text, where I had error printed by p_error, and then it appended the colon space, and then its text, and it came back as no such file or directory. We got the same message back using the string error function. So the second example here is going to be a divide by 0. So here I have my function divide by 0, and here I have my divisor, and if my divisor is actually is 0, then I say, hey, that's no good, and I'm going to use the exit function and pass a -1, because -1 indicates we were not successful. Otherwise, if the value of my divisor is not 0, I am going to perform the actual division and output the result. Here we can pass an exit 0 and end the program right in this function if we chose, by passing the value of 0 to the exit function indicating it was successful. So the first time I'm going to run this without an error, and it was a successful division. So let's make that divisor a 0. And it says, no, you can't do that. And look, our process returned a -1, so that means it was not successful. So the last example here is this exit status, and this is just demonstrating using macros.